Okay, this next session is a hands-on session covering single subject linear regression based on the same data you've already used. The PDF for it you see is AFNI 05 regression.pdf. And just so we all start on the same page, I'll note that in my home directory here I have the AFNI handouts directory, which has all the PDFs and text files that we cover for this class. And I will just open it using AFNI Open, which is an AFNI program that looks through the directories in your path to find certain viewing functions for PDFs. So in my case, it'll probably use events on a Mac. It'll work similar to just the open command. But anyway, so we can all use the same one. I'll say AFNI Open, AFNI Handouts, AFNI 05, regression.pdf. So what you have hopefully covered to this point is using the AFNI GUI interactively, since we will be doing some of that in this class. And you've covered the hemodynamic response function using fixed shape basis functions, or probably even variable shape basis functions at this point. But for this particular class, we will stick with the fixed shape basis function, which means we assume that the brain responds with the same shape to every stimulus, regardless of the location in the brain, regardless of whether it's the third stimulus or the 17th one, regardless of the subject. So we'll assume a very fixed shape response, and the only thing we are estimating is the magnitude of that response. So the magnitude for that response is a beta weight, and along with that beta weight, we get maybe a t-stat for its significance. So in this hand-on session, we'll discuss pre-processing steps lightly. We'll go into that more detail in the start to finish class. But we'll cover, you've covered the regressors and the design matrix and that, so we will talk about it more from a practical sense, looking at it closely and making sure that we understand what components are in the regression matrix. And then we'll do some navigation with the GUI, looking at the data, and just covering the results. Anyway, so the Voxelwise regression model that you've presumably just reviewed, y equals x beta plus epsilon, the x matrix is the regression matrix, which is a list, the columns of which you might say are the regressors of interest, of no interest, the baseline model, everything put together in one regression matrix. And in order to fit that model to the data y, we have beta weights for each regressor, which say how much of each regressor was used to make that fit for that current voxel. And then we fail to match our current voxel's time series by some epsilon time series. So x beta gives us our fit, and the difference between y and x beta is the residual. So we'll have our HDR, hemodynamic response regressors. Those will be our main regressors of interest. Beyond that, we will have drift effect estimated with polynomials, and we'll have some motion parameters in there as well. But this is a very simple example just to get us started. I think that's okay for this. We'll come back and talk a little bit about the difference between ordinary least squares with 3D convolve and the ARMA 1.1 model, which uses 3D Remel fit. So in this case, our data is a speech perception task. We got this data from Mike Beauchamp's group, and the subjects are presented with audiovisual stimuli, and they're basically two types of stimuli which are almost the same. So they're like short video clips of people saying simple words like cat, and then they'll say this for like 20 seconds at a time, and then there will be fixation between them. However, to distinguish the two classes, in one case, the audio aspect of the stimulus is reliable in that you can hear the word clearly, but the visual aspect is degraded a bit. In the other case, the visual aspect is reliable. You have a nice clear image there, but perhaps you can't hear the word so well. And then of course, perhaps the contrast of interest will be just which voxels respond differentially to these stimuli. So we have, for design, we have 3 runs. And remember, a run is just when you press start on the scanner, it makes the loud noise while it's acquiring data for a while, and then you press stop, and that's 1 run. And in this case, there are 3 runs of data, so we have 3 echoplanar imaging data sets, and within 1 single run, we have 10 randomized blocks. 5 blocks are auditory reliable stimuli, and 5 are for visual reliable. And those are pseudo-randomized within the block. So there are 10 trials within each run, and each single trial, we'll call that a single stimulus in this case, lasts for 20 seconds. To be a little more nitpicky, you could say it's a bunch of 1-second stimuli that's like 1 second on, 1 second off, approximately, because the words, even the words differ in their lengths and how long it takes to say them. But it's basically 1 second on, 1 second off. And if you just ignore the minor fluctuations due to that, you can pretend this is a 19-second stimulus or maybe a 20-second. Will just be simple in this case. And then, so 1 single event is 20 seconds on, and then our baseline condition is just 10-second fixations between those. So one thing you might note about this is the main stimuli, they are all visual, they are all auditory, and they're contrasted with a baseline that's just a simple fixation. So the responses to this in the audio and visual areas will be strong. That's why it's good for a class demonstration. The actual data acquired, there were 2 anatomical scans. That was because the intention was to do a surface-based analysis, and maybe they wanted to register these 2 anatomical data sets and average them to get noise reduction before running FreeSurfer. But we will not do that today. And beyond the anatomical scans, we have 3 EPI runs. For 1 EPI volume, there were 33 slices, and then we acquired, or they acquired 152 volumes per run. And we're going to drop the first 2 volumes per run as like pre-magnetization steady state time. That's only 4 seconds worth. Usually you drop at least 7, maybe 10 or 12. In this case, we didn't get any pre-steady state data, so we kind of faked it, so we only faked 2 volumes. That's good enough. So the TR here is 2 seconds. That's why I said the 2 volumes was 4 seconds of data. And the voxel dimensions are 2.75 millimeters squared within plane, and then 3 millimeters between slices. The sample size, we had 10 subjects in our group. Far too few to do any real analysis, but it's good enough for this class demonstration. Also because the responses are so robust with these strong stimuli, that's enough to do a reasonable group analysis. So now we'll shift to the AFNI GUI and just follow along on this page. So since you can stop and start this at any time, I will just go through it fairly quickly myself. So first thing, I'll just minimize this a bit. I'll try to keep the slide large enough to read here. Hopefully that's good. And now we're going to go to the data directory, AFNI data6/AFNI, and then we'll run the AFNI graphical user interface, the GUI. So in my home directory, I have AFNI data6. That's the typical way we set it up. cd AFNI data6/AFNI. And after typing cd, we always want to get in the habit of typing ls just to see what files are there. So we have an anatomical data set. We have one in standard space. Here's EPI run 1 plus orig. So that's actually, that's our EPI data that we are going to look at right now. So the prefix for this data set is EPI R1. It's in the original space, which is to say we haven't aligned it to any template or anything yet. And then we have the brick extension. That's the raw data. That's just 3D volumes of short integers in this case by 152 time points. And then the head file is just a text file that describes the data, where it is in space, the slice timing, the TR, things like that. So beyond that, perhaps the two files of interest might be stimulus timing files, when our stimuli happened, and then an ideal regressor. In this first part, we're just going to look at a single ideal time series. So let's just follow the slides at this point. So we'll run AFNI here, and we'll set our underlay to EPI run 1. We'll open an axial image and graph, and then we'll pick an ideal and look at it. So we'll set our underlay to EPI run 1. You see there are 152 time points here. And I'm going to close a couple of these windows just to save a little screen space, and then these can be a touch larger. And open an axial image window and a graph window. And now we can pick our ideal time series, which is EPI run 1 ideal. You notice our ideal time series, as you see in the window there, it's just a single curve that doesn't seem to have any long breaks in it. So actually in this case, our EPI ideal is a combination of both the audio and visual stimulus conditions, but we just put them together so we can do a quick demonstration at this point. So under FIM, in the graph window, we want to pick ideal, and the ideal we pick, I'll do that again just to be clear. So we'll click on the FIM button at the bottom of the axial graph window, and that pulls up a little menu, and the top item in the menu is pick ideal. Click pick ideal, and now we can select EPI R1 ideal.1D. You notice this has 152 time points as well. So then we can hit set, and beautiful, we see the time curve in there. So that in some sense is what we expect to use as our ideal regressor for this run. Again, it's a combination of the two audio and visual stimulus ideal curves. So once we've done that, we're going to jump to the same location in the data set so we see, so we all see the same data. So it says right-click on the image, jump to IJK, and then go to 2672.4 and then hit set. So in the image window, you can right-click and jump to XYZ or jump to IJK. XYZ, we could jump to coordinates, DICOM coordinates or LPI coordinates, depending on how you specify it. In this case, we're jumping to indices, IJK. So remember, this is a matrix. A single volume is a matrix of 33 slices, and if we do 3D info on EPI R1 plus orig, I made made that disappear too quickly. If we do 3D info on API R1 plus a ridge, you can see that a single slice is 80 voxels on a side, and then we have 33 slices within one volume. So if you imagine a single slice, the indices, since this is RAI, this is going right to left, anterior to posterior is the orientation. That means index 26 should be going from starting at 0. It should be going from right to left, 26 times 2.75 millimeters from the left edge. So index 72 is the J position. That's in the AP direction. So out of 80 voxels, 0 through 79, we're going to part index 72. And then the slice is number 4. So 0, 1, 2, 3, 4, counting from the bottom. Because this is RAI, it should go 0, 1, 2, 3, 4, starting at the most inferior slice. So fantastic. Let's do that. So in the image window, we'll right-click, and then we can jump to IJK and type in those numbers. 26 space 72 space 4. And again, if you hit apply, it happens, but this little window stays here. If you hit set, the action happens as well. It's like hitting apply, but then the window disappears. It's like hitting apply and then quit. And there we go. So we're at those IJK positions. If you can read this fountain here in the graph window in the lower left, you see the IJK indices 26, 72, 4 match those in the handout. And the time series does not quite match that in the handout. Oh, that's interesting. I never even realized this. In the handout, they must be viewing the data with left equals right. Here in my .afnirc file, I've set the environment variable to keep the left side of the brain on the left side of my image viewer. So we are on the right side of the brain now. In the graph window here, it looks like these are reversed. The voxels are reversed. So they must have been on left equals right there. Anyway, other than that, we are looking at the same information here. So now we want to just focus on what's interesting. So spikes are interesting. Spikes have a big impact on any analysis that we run. And if you notice, many of these voxels start with this big spike in the very beginning of the run. And what is that? That's generally because of the scanner hasn't reached steady state for the magnetization yet. So especially time point 0, the first volume is much brighter than the other ones. And you might even notice typically in the first volume, in like a sagittal or corona image, you'll see like window striping on it, similar to what you might see for a large motion. We don't see that here because we weren't that picky when we had to fake these first 2 volumes, just making them a little randomly brighter than the others. And so we don't see the striping here. We didn't go that far. But typically with real data you would. Anyway, so the spike at the beginning is from steady state volumes. And then we have the spike down here. If you want to see what happens there, it's actually helpful to look at the sagittal image, because the typical cause for mid-run spikes is subject motion. Now, there could be other reasons, but that's the most common one. Now, you can either use the greater than or less than keys to go over there, scroll over there in time. That's entirely too much work. I could just click somewhere around here until I find that spike, and then a few keystrokes to bring me right on top of it. Or I could even type in a number here. I'm going to start at 40, and that's close enough. Then I'll use the right and left arrow keys to see what happens to the image as we move around that spiked time point. So I'll hit some greater than symbols, and I see, oh yeah, that's just head motion. And in fact, with this irritating data, the subject didn't actually move. They were too good, so we didn't want such a good subject for the class, so we had to fix that up too. We faked a little bit of head motion, so we added a 2-degree rotation for that volume. But anyway, so you see approximately what would be a typical effect of head motion here. And again, you don't see the striping because we faked it. And adding striping would be entirely too much work. So let's see what else is on the slide here. So we have, you see in the data, the actual acquired data, that's the black curve, and the ideal time series, what we hope to see as a response to our stimuli, is the red curve. You see that these are pretty well locked. If I reduce the matrix size with a couple of little M keys in the graph window, and just to quickly remind you of that, if you go under the opt menu in the lower right corner, there's some scaling keys and matrix keys underneath that, and you see you can reduce the matrix size, make it greater, or you can specify a number like 5 here, but the little m and big M here are keyboard shortcuts. So if I hit a little m, well, I'll reduce the number of the size of the matrix, and a capital M makes it go up. What you can see in the axial image window that corresponds to this graph is a box here. I'm going to change the color of the crosshairs to blue. Is that more visible a little bit? That's good enough. So you can see the size of this box corresponds to the number of time series in this graph window. It's getting huge now. And if I just click a bunch of little m's, it'll get small down to a central voxel. So this is our time series, and you notice at this voxel we have a very nice response. Aside from the pre-steady state spike and aside from the motion spike, this is beautiful. So clearly we're at a voxel that where the subject's brain at this location seems to be showing a bold response to our stimuli. And let's see what else is in here. We have head motion, scaling, so you can hit, again in the graph window, right now it's scaled automatically, but you can do plus and minus to make it taller or shorter. Let me show a few more voxels that may make it more easy to understand. So I'll do a couple minuses to scale them down, a couple pluses to scale them up, way too big, an A to scale them to fit the window, as well as the plotting software thinks it should do. So like it scales the window. In this case, the minimum and maximum values are kind of controlled by those spikes. If we ignore a couple time points, it'll be much more clear. And let's do that since we're here. You can ignore them under the FIM menu. There's an ignore, and you can come over here and type a number in, and that's the number of time points it will ignore at the beginning. Or I'm going to use a keyboard shortcut. In the graph window, I'm going to hit a capital I to increase the ignore value. So I'll hit 1 I, 2 I's, and now I'm ignoring 2 time points. If we go back under back under FIM, ignore, now you see the values up to 2. So that's just that's a nice keystroke for doing that. As long as we're on it, where do I get these keystrokes? One place, you can come over in the main AFNI GUI and hit AFNI tips, and in this window you can see a lot of keyboard shortcuts. And for example, here, keyboard shortcuts for the graph viewing window. If I click on that, here's a whole list of them. And in this case, I hit a capital I. And you can see lowercase I decrease the graph ignore by 1, uppercase increase it by 1. So that's what we just did. And just to note, this window here, oh, that didn't come up. Didn't look so pretty this time. Oh, interesting. That looks kind of bad. Anyway, so this is just now I'm looking at differences for laptops. But just a reminder, on some machines, like if you're going for keyboard shortcuts and help windows, a lot of this stuff will be shown under a hidden window that you might be able to use the AFNI cursor to help detect. But for the most part, you just learn where they are. Like right here, there's a hidden window, and if I right-click here, I get a whole list of things I can do. So back to this, we just ignored a couple time points, and now we can see if I drop the matrix size. Why is this scaled down so low? Okay, I'll hit A to automatically scale it, and now we see ignoring that spike might make it look better. Actually, with the red curve on top, I think that squishes it down a little bit in any case. But here you see, now with ignoring the 2 time points, you see a better fit with that red curve. So that's it with the data quality check. I think I will end this video here, and then we will continue on the next slide with preparing for data analysis, some of the pre-processing steps. We'll continue that in the next video. Thank you.